So I was looking at what I did last week when we started talking about damped oscillators. Dude, what an embarrassment. I did it really poorly. I got to do it right. I got to go back and clean up my mess. Let's go do that. So here we go. So this is what I was thinking here. What I'm thinking here is that when deriving the second order equation, we saw that the left side had an operator equation. Sometimes I call it the operator matrix. Sometimes I call it the cofactors. And of course, X is either going to be VC or IL. And then the constants on the right are the effective sources. So what we find here, it is the operator matrix or equation that gives us the details. Look at that. Gives us the deals. What's up with that? Let's erase that. How about if I just do this? I'm not going to have space. Details on the natural response of the circuit. Both the cap and the inductor have the exact same natural response because they both have the same operator matrix. And you can't see that with the direct method, right? The direct method hides all that stuff. That's not the case with the operator method. It's there for everybody to see. So that's an important piece of information right there. So then we went into the undamped and damped harmonic oscillator. So if I looked at an undamped oscillator, that means that the acceleration due to gravity is 0, is what I'm setting it, just to make it nice and easy. What does the force of gravity do? All it does is it just changes the equilibrium point. It doesn't really matter. But just for the sake of simplicity, I just said, G is equal to 0, so that way we don't have to include it into our force equation. So when I apply N2L, I know that the net force, look at this, where's the M coming from, dude? That's an X. It's the spring force, and that has to equal, of course, mass times acceleration. So if you clean this up, you get this here. Now, the proper solution that you probably learned, not the one that I was showing you, is going to say that the solution then is going to be A1 times e to the S1t plus A2 times e to the S2t, which is different than I said before. And I think that the way I was stating it was a little bit more advanced. And what you find here is you get a solution that kind of looks like this here. Okay, and this is really the quadratic equation applied to this differential equation here. So you could modify this solution where instead of having A1 and A2, you could get A and a phase constant. And then that's the solution right there. So what's the characteristics of an undamped oscillator? Well, it oscillates forever with no damping, since there's a perfect exchange of kinetic and potential energy. So when I look at this guy, it's going to look exactly like this. So what I did here is that the key thing is this equation and this quadratic solution here. So what I want to do here is that I want to come in and I want to show you an applet so you can see what I'm talking about. So in the applet, you get a differential equation that looks like this here. You get a differential equation and because remember, this guy tells us right here is that this is what? We're looking only at the natural response. And if you'd rather, you could call it the homogeneous response. So what I'm going to do here in this applet, I'm going to set A equal to 1. And I'm going to set B equal to 0. So when I set B equal to 0, and in this case, I'll probably, I don't know what I set C. I'll set C equal to 1. It doesn't really matter what the value is. When I set this B equal to 0 here, what this means here is that there's no damping. since damping forces typically are proportional to velocity. So then let's go look at this thing. So if I go share my screen with you, it looks like this. So what I got to do here is that here's, so A, I'm going to set to 1. There's the mass. So the damping, I got to set to 0. So if I set this to 0, it doesn't allow me to just type the damn thing in here. And you could see that I have an oscillation that is perfect. It's undamped oscillatory motion. And when you look down here at the bottom, what you're seeing here is that you're getting that you're looking at that quadratic equation and you're getting these values for the solutions to these guys here. Okay, so that's what that looks like here. Now what I want to go back do here is I want to go back. So I just copied and pasted that image. Now I just got to find my OneNote. Okay, so we're back to my OneNote. So that's all I did right here. Let me make this so you could see here that you get perfect oscillations. So now the next thing that I want to do is I want to go look at damping. Okay. And so our first case here, how did I write this? I said case 1 is undamped. Now I want to do damping. So then case 2, I want to do damped oscillations. So when I look at damped oscillations, essentially what we were talking about is that you could imagine that I have an oscillator. And this time we're going to put it in water or some fluid, right? So if I put this in some fluid like this, we could imagine that this guy's going to be moving. So it's going to look something like this here. And so what we're saying here is that if I have damping, implies that you're moving through a fluid. Right? It's not friction, it's a fluid. And we could say here that we're going to look at laminar flow here. So when I look at this damping term, I'm imagining it looks something like this. And that's where you get that B term. So now if I go in and apply Newton's second law, what you're going to find here is that our net force now has 2 terms. It has a spring force, and now there's this damping term, and that equals mass times the acceleration. So in a very analogous way, we could imagine then if I go and I look at the solution, it's got to be the same type of solution here. So then if I look at the solution, as we did before here, the solution in this case should tell us that we should get x of t, and I'm going to get a1 e to the s1t plus a2 e to the s2t, where now the solutions of S1 and S2 are these so-called characteristic roots. So it should read minus b squared plus or minus the square root of b squared minus 4ac divided by 2a. Now the thing that you got to remember here is that we set a equal to 1. Okay. So if we're talking about a equal to 1, then you're going to see that this really reads like this. So what we're saying here is that the important piece is the stuff under the square root. And when you look at the square root term, you could see here is that the square root term reads b squared minus 4c. That's the important term. And the possible solutions come in 3 flavors. Okay, so the first one that we want to look at, right? So the first one here is that, so if I look at the solution, one solution would be b squared equals to 4c. When you have this solution, this is what they call critical damping. So if I go back and I look at critical damping here, what am I going to see here? Well, here, what I'm going to do in this case here, here's what I'm going to do. So what I'm going to do in the applet, I'm going to set, again, I always start with a equal to 1. And then I'm going to set b equal to 2 and c equal to 1. And you could see here that b squared, which is 4c, of course, this is going to be 4. So then that means I'm always going to get, that gives me 4 minus 4, which is 0. Right? So if I actually put that in, maybe I should write it this way instead. I'm going to get this guy here, which tells me that the roots has to be 4. So now let's go do that in the applet. So I'm going to go do a new share. So what I'm going to do now is I'm keeping C at 1. So I just need to change B to 2. And if I go B equals to 2, I can never get it there. Oh man, I had it. Damn. Okay. Come on, baby. Oh yeah, there you go. It's critically damped. And you could see here is that look at the solutions. The solutions are exactly the same. So then I know how to calculate this thing. And of course, if they're the same solution, you have to have a linear combination of solutions. So then you get that thing right there. So what I'm doing here is that I'm copying this thing. And then I'm just pasting it into the OneNote here. So let me go change my share. And so you could see I copied it. And that's what you would be getting right there. So then the other solutions is then going to be 2 is that you have b squared greater than 4c. When you have this, then the radical, right? The radical is positive. You know, maybe I should do this here. How about if I do this? So if I look at this here, square root, this guy has to be greater than 0, which implies that b squared has to be greater than 4c. And when you get that, you get overdamped. So you have an overdamped oscillation here. So what I'll do in the applet here, the only thing that I'm going to do here is that I'm going to keep, and what I'll do here is that I'll keep A equal to 1. I'm going to keep C exactly the same now, but B now, I'm going to make it smaller. No, I'm going to make it bigger. What am I doing smaller? I'm going to make that bigger, and then C, I'm always going to keep it like this. So there's only one parameter I got to change. Let's see if I can do it this time. So here we go. So if I go do the share, okay, so this guy just got to make it bigger, right? There we go. So you could see that that's underdamped, right? There it is, underdamped. And what you're seeing here is that the solutions to S1 and S2 now are real. So let me go copy this and put it into our OneNote. So you're seeing what I'm seeing. Okay. And so then the last one is that when you look at that radical, right, there's the, you can see I just pasted the overdamped. So then the last case, what you could have here is it turns out that B squared minus 4C, this guy is complex. And the only way you can get this to be complex here is that if B squared is less than 4C, and if you do that, complex roots tells you that it must be underdamped. So I have underdamped oscillations. So what you're going to see in this scenario here, what I'm going to do here is that I just need to make B smaller than 4. So I could pick any number. So if I go to the applet again, I'm setting, again, A is equal to 1. I'm keeping C equal to 1. And then I'm just going to make this some value less than, to make sure that it's less. So if I go do that share, you could see that if, wait, didn't I already, am I screwing up or something? Why is, this is, am I looking at the, oh, it's 5. I kept thinking it was 0.5. I was going like, that solution is wrong. Yeah, but I just got to pick some number here. Right? And what you're seeing here is that, look what's happening right there. This number is less than that, so I'm going to get some oscillation. So then if I go back into my, go back onto my screen here, and I look at this guy, you could see here that now, let me go get this guy here. I was able to change it to 0.5 here real quick. And then this is what I have. I get underdamped oscillations. Exactly what the equation tells us here. So when we're looking at these oscillations, you could see that there are 3 possible oscillations. And what I started saying here is that what's special about this thing here is that now applying these to the RLC circuit, we then have 2 cases as well. We have case 1, which is an undamped LC circuit. And what we showed this here, right? So in other words, there's no resistance. And what you're finding in this case, which is what I showed you last time, is that I had a capacitor, an inductor will oscillate the E and B field energy between them. So that is exactly as an undamped oscillator here. And what you're going to find next here is that if I now go to case 2, now I'm going to have a damped RLC. And the reason why it's damped is because the resistor will take energy out of the system. And so you get these types of damping here. And what you're going to find here is that when you look at this thing here, I can't really tell you what parameters do, because each circuit has a unique differential equation. And because they have a unique differential equation, we have to account for that. But ultimately, this is what we know. What we know here is that if I have some oscillation, let's say it looks like this, what you're going to find is that there is a critically damped one. And critically damped essentially means that it goes to 0 the fastest. Okay? So in other words, this guy right here is the critically damped. And then I have a much slower one, and the much slower one is overdamped, which means it takes a lot longer to go to 0 actually. And in this case, this guy right here is overdamped. And then finally, I could have underdamped, which means then that it's just then going to oscillate until it damps out. And this would be underdamped. So you get the same kind of oscillation as before. So here we go. So what we're going to do here is that we're going to do the following thing. So now that I have an RLC circuit here, so to distinguish between the types of damping in RLC circuits, we must solve the characteristic equation. And I'm pretty sure from past experience that this is what you did in Math 7, right? You solved the characteristic equation to get the characteristic roots. So what do I mean by that? Here we go. So what we said here is that I have an operator matrix. And that operator matrix is going to be operating on x1 and x2. And this is equal to 0. So remember, this is the homogeneous solution, right? This implies that we're only looking at natural response. And this guy, this is the important piece, okay? It's the operator matrix that's going to tell us about the characteristic equation. So what we're going to do here is that we're going to go like this here. So this implies here is that dx, the operator matrix is going to look something like this here. And we're going to rewrite it to be in this form right here. Okay, this is the definition. So this is what I'm now going to call proper form. And this guy is really nice, okay? You know what? I'm going to write this a little bit different just to keep it a little bit cleaner. So what I'm going to do here is I'm going to say that if I want the natural response, then this we're going to define like this. So it's going to be operating on the natural response, and this is going to be equal to 0. And what you're going to see here is that this is the form of the characteristic equation. So now that I have this characteristic equation, what we do here is that we define alpha. It's known as the Napier frequency, and omega naught is the natural frequency, which are two things that we actually measure in the lab. So starting with this here, what we do here is that we now assume a solution form of x to the m, a e to the st. And when you do that, you're going to find here, so we assume a solution and substitute into our second order equation. And when you do that, this is what you get. You get s hat squared plus 2 alpha s hat operating on what? This solution right here, which is a e to the st. And so when you do that, you get this solution that looks like this. Times a e to the st equals to 0. And the only way this can be true here, right? The only way this can be true here is that not that a times e to the st is equal to 0, but the parentheses term. And so therefore, s squared plus 2 alpha s plus omega naught squared equal to 0 is therefore our characteristic equation. And so then we need the roots for this. So then next, the solution to the characteristic is then going to be this here. So check this out. There's a reason why we want it in this form, right? This tells us then that the solutions are then going to be something like this. It's going to be S1, 2 is then going to be minus alpha plus or minus alpha squared omega naught squared square root. So where the natural response now is then going to be A1 e to the S1t plus A2 e to the S2t. So these guys are now interconnected here. This is the characteristic roots, and this guy is the general natural response. So you can't separate these two solutions. So right away, we could then go back to what we were talking about with the applet. And you could immediately see that there are three cases, right? By looking at the square root term, there are three cases. Well, the first case will be when alpha is greater than omega naught. The second case is when alpha is equal to omega naught. And the third case is when alpha is less than omega naught. I really should be squaring these terms, but I think I could get away with that. And so here we go. So then I'm just going to follow the math, you know. So if I have alpha equal to omega naught, which is the easiest one, then this implies here is that the characteristics roots are equal. That's a critical one, right? So that means S1 is equal to S2. So when I look at this thing here, then that means S1 and S2 in this case is going to be minus alpha plus or minus 0. So therefore, they're equal to minus alpha, both of them. If this is the case here, then our critical solution from math 7 here must look like this now. And so that's what we mean when we do this. Oh, I forgot to write this. This implies critical damping. Right? That's the solution. Then if I go to case 2, then I start to look at them differently. So then if alpha is greater than omega naught, then what do we know? The characteristic roots are real and distinct or different. In other words, S1 is not equal to S2, but these guys are real, and this is what we call overdamp. So in other words, I'm going to have S1, in this case, will then be minus alpha plus alpha squared minus omega naught squared square root. And then I'm going to have S2, which will be minus alpha with the minus sign this time, minus the radical. So then when I look at the solution to this guy, then I'm going to have overdamped, and this solution then reads a e to the s1t plus a e to the s2t, where I call that my damping constants 1 and 2. So now we have our second one. And then our final case is case 3, is when alpha is less than omega naught. In this situation here, you're going to find that the characteristic roots are what? They're complex instead of real. So the characteristic roots are complex and also distinct. Again, in this case here, you still have S1 not equal to S2. And in this scenario here, this is, of course, the underdamped. So when I write the solution for these guys, what you're finding here is that now I have complex roots. And so we typically define a new parameter called omega d. And you might guess what omega d has to look like. So I get S1, and then I write this as minus alpha. And then look how I write this. I write this as plus j omega naught minus alpha squared square root. And then we typically define this term, the square root term, as omega d. But for right now, I'm not going to do that. But until I write the solution, no, we should be really careful here. In this case, because we use I for current, we typically define J as the square root of minus 1. So then if I go and I look at this guy, the underdamped is then going to look, it's going to be oscillatory, so it has to look something like this. So I'll write N1 cosine of omega d, A2 sine of omega dt, where omega d is then omega naught squared minus alpha squared square root. So then this gives us our second or our third scenario here. Okay, so now that we have that, I want to go look at the strategies. Let me see if I looked at that. If I wrote, damn, I thought I highlighted those strategies. Oh, give me a second. Let me go find them. Here we go. So now what I want to do here is that I want to go in and I want to look at my strategies for step 2. So what you want to do here is that in step 2, you determine the characteristic roots where you start with that operator matrix. You get the root, the equation, you get the roots, and then you define them. And then you go and write out the general solution, which means that you know the constant b from step 1. And the only unknown constants that you should not know in this equation is A1 and A2. So to stress this idea, what I'd like to do here is I'd like to go in and look at the next example. Okay, let's go look at the next example. And in this next example, what we want to do here is that we're going to look at example 8.3. So there's a part A, B, and C. So let's go do this. Okay, so what I'm going to do here, in all 3 of examples, what I'm going to assume here is that because there's no step function or anything, I'm always going to assume these guys to be 0. Okay, so here we go. Let's go do this. Let's go derive the differential equation. I'm going to derive the differential equation 3 times. Why am I doing this? Your ass better gets that differential equation right. That's the important piece. Okay, here we go. So I'm going to look here. I'm going to look at KCL. I'm going to look at KVL. And right away, I could see the inductor current and the capacitor current are going to be the same. So here I go. So I'm going to write IL must be the same as IC. I'm going to keep writing this. So I get IL. Then I'm going to convert C, the current, into a voltage. So then I'm going to say, look at this. So it's 1 over C. So that gives me 2 S hat VC. Any resistors? Nope, that's 0. That's my first equation right there. Let's go to the KVL. So when I look at the KVL, you could see that I should be going all the way around the outside. Nope. What do you mean? That's not a voltage source. It's got to be this loop right in here. So I'm going to do that loop on the right hand. So let's go do it then. So here I go. So I could see here that the voltage across the 1 ohm must be the same as the voltage of the inductor plus the voltage of the cap. Okay, here I go. So what I'm going to do here is that I'm going to bring the 1 over to the other side. So I get VC, and then I'm going to get minus, oh, no, let's see. I have the inductor here, so I'm going to convert the inductor. So the inductor is a 2, so it should be 2 S hat IL, and then I have minus the 1. So let's focus on the 1. If I look at the 1, if I apply KCL at this node right here, you could see at this node I have I source, I1 ohm, and then I get the current of the inductor. So this is a 1 ohm resistor, so it's going to be 1 times KCL tells me it's I source minus IL. Let's clean this up. So I'm going to clean this up. So let's say that I move all of the VCs to the right. So I'm going to go VC. Now I'm going to collect IL terms. Look at my IL terms. There's one right here. There's one right there. There's only one VC. So then I'm going to go, if I do this, I'm going to get 1 plus 2 S hat IL. And then look at my source term. I got to take it to the other side. So then my source then becomes IS. Here's my second equation right here. Let's matrix this. So here's my matrix. So I'm going to collect all the VCs here. So look at the first term. I'm going to take a minus sign. So the first term is going to read 2 S hat. IL is then going to be minus 1. Look at the second equation. I'm going to get 1. Now look at this guy. I'm going to get 1 plus 2 S hat. So then this gives me VC, IL. Look at the source. It's going to be on that side here. Now let's do the matrix here. So remember, this is D here, right? This is my operator equation right here. This is D hat. So what am I solving for? What did they say? They want the inductor equation, right? I need the inductor current. So I got to write this for the inductor current. So let's go do this here. So the inductor current is the second one. So look what I'm going to do now. So it's going to be the inductor current times this. Now I take my constants, and remember, this right here is my IL term. So I take my constant, my effective sources, and I put it into there. So then this guy's going to be 2 S hat, 1, 0, IS. And I got to take that matrix right there. So if I look at this thing, let's go do this here now. So what I'm going to do now is that I'm going to do the cross product for the operator matrix. So here I go. So D is then going to be 2 S hat operating on 1 plus 2 S hat. Then minus 1. So I'm going to get minus 1 operating on IL. And then this guy's going to look like what here now? So I got all positives here. So let's check this out. You know what? I'm going to move this all the way because I'm going to run out of space.
Hey, Carlos.
Yes.
I think we might have some sign errors.
Where do I have sign errors?
Well, so that first equation is IL minus, I think that should be 1/2, right? Because the capacitor is half a farad.
Where are you looking at?
The first equation, the KCL. We converted IC. So shouldn't it be 1/2?
Yeah, but what's 1 divided by 0.5?
But
it's 2.
Oh.
Right?
Oh, yeah. Sorry, my bad.
No problem. No, keep my ass honest, dude. I know I'm going to be making mistakes. Help me out, please. So then let's keep going.
But actually, wait, so then with matrix, I think, shouldn't the minuses be flipped on that first row?
Yeah, but remember, it's equal to 0. So if I multiply everything by -1, it flips it this way.
Oh, got it. Sorry.
Okay, no problem. Again, keep asking those questions. I don't
No,
trust
but wait,
me.
why 1 over C?
Say that again.
Why is it 1 over the capacitance?
Why is IC equal to 1 over C S hat VC?
Well,
I think that's
no, that's IL.
okay.
Yes.
Okay, let me put a C here then.
So if it's IC, isn't it C S hat VC?
IC. Oh, damn. Did I flip this thing?
Yeah, because the 1 over C is for the S
Oh,
inverse.
hey, Josh, you were right. So this is
That's
1/2. I told you you shouldn't trust me. So there's 1/2. So then I got 1/2 right here then, right? Any other mistakes? I think I'm clean right now. Damn, I'm flipping the thing. Okay, so let's start moving here. So look at the first term. So what I'm going to combine right now is I'm going to combine this guy with this guy. That's going to give me my square term. So this guy should be what? S hat squared. Then my second term, so I'm going to combine this guy and this guy here. That should be 1/2 S hat. So I should get 1/2 S hat, right? And then I should get +1. And then this should be IL. Now let's go do the matrix here. The matrix that I have here, let me make sure that I didn't mess up with this 2 here. That looks good. That looks like this should be 2 S hat I source plus 0, but we're going to assume a constant source. So therefore, this should give me 0.
No, I think it's also 1/2 instead of 2.
Is it 1/2?
Because we're replacing the second column, but the first column stays the same.
So let's go look at that. So VL should be L S hat IL. What is L?
Oh, wait, let me see.
It's 2. That's where that 2 is coming from. Is that not
Yeah.
right?
But I'm looking at the determinant of the right-hand side of the equation.
Oh, that's the 1/2. That's right. That's a 1/2 right there. Yes, that is. So there should be a 1/2 right there. But if I source is a constant, we should be equal to 0. By the way, we should check this. Is that what I wrote? Where is it at? Yeah, okay, that covers that. So now that means here's my second order equation then. So I got S hat squared plus 1/2 S plus 1 IL equal to 0. That's my differential equation right there. Okay, so if that's my differential equation, I want to do a check and get force response. Well, clearly, if I choose that to be my force response, then that tells me that the first term, right? So if I look at this guy here, it tells me that I get S squared times B plus 1/2 SB, and clearly these guys have to be 0. So then, of course, I'm going to get B equal to 0, which tells me that B is equal to 0. So therefore, the inductor force response has to be 0. Now, is that true? Let's go look at this equation. When the capacitor opens, we see that the current of the inductor goes to 0. So if I check this with circuit, as cap is open, IL of infinity is 0. So that checks out. So here we go. So when I look at this thing, here's what I'm seeing here. So we know that this guy right here is the natural response. I'm sorry. So the characteristic equation is then going to be s squared plus 1/2 s plus 1 equal to 0. That's our characteristic equation. So what I'm going to do here is that if I can't get the roots of this equation right away, I'm not even going to try. So I'll tell you what I typically do. So once again, if I can't get these roots right away, I immediately go in and compare this to this guy right here. So if I do that, this is what I see here. I clearly see, I'm going the wrong way again, is that if I do this, this immediately tells me that 2 alpha has to be 1/2 and omega naught squared has to equal to 1. So this tells us right away that alpha here has to be 1/4 and omega naught has to be 1. So therefore this tells me here that omega naught is greater than alpha, which then tells me that it's underdamped. So it's underdamped. So when I have underdamped, again, this is the key thing here. The fact that I have this is underdamped. So now I immediately just start turning the crank, right? I start turning the crank. And when I do that, one of the important constants for underdamped is omega d. So if I go and I compute this, this guy's going to be equal to 1 minus 4 squared and if you put that into a calculator, I end up getting this guy right here. So now I know what omega d is. So now what I'm going to do here is I'm going to write out the natural response. So then step point 2.2, write out the natural response. So the natural response, because it's underdamped, all I do is I just go here and I go, well, if it's underdamped, oh man, there's a typo here. This should have the arrow going the other way. So this guy should be going like this. So it has to be that third case. So I get the cosine and sine terms. So therefore, I then write that IL of n of t should then be e to the minus alpha t times a1 cosine omega dt plus a2 sine omega dt. So then if I start to do this, this is going to be then e, look at alpha, it's a quarter, so it's got to be t4. Then I'm going to get a1 cosine of 0.968t plus a2 sine 0.968t. That's my underdamped solution. Now I write out the general response. And the general response in our case then says that the inductor current is now going to be the natural plus the force response. So what's the natural? It's got to be e to the minus t4, right? A1 cosine 0.968t plus a2 sine 0.968t plus b, right? B is our force response, but we already saw that b was equal to 0. So now we have our complete general response. So now we're set up later on to then apply the initial conditions to get A1 and A2. So I want to do the exact same thing again. And in this case, I'm going to go to B. So here's B. Okay, let's go derive this guy. Okay, let's see how I
Carlos,
do on
could you
this
scroll
one.
up for just a second?
Yeah. I didn't hear what you said.
Could you scroll up for just a second?
Sure. So what you're seeing in this
Thank you.
case here is that I have my inductor. You could see that all of these are essentially parallel. So you could see that a big piece of this guy is that I'm going to have to use KCl to get the current, to connect the current of the 4 ohm, the inductor, and the cap. And then I got to do KVL to connect these two voltages right there. So let's go do that. Okay, here we go. So I'm going to start with KCl now. So I got to relate IC, IL. So then I'm, like I said before, I'm going to apply KCl to the red node. So then look what I'm going to do. I have the current of the 4 ohm, current of the inductor, current of the cap. Now I know that all of this is equal to 5. So I'll put 5 at the very end. So again, right? I4, IL, IC. So now I got to change the resistor and I got to change the current of the cap. So let's go do that. So note that the 4 ohm resistor is in parallel to the cap voltage. So in this case here, you could see that I could write this node as VC of T, where this guy right here is my ground. So my top node, I'm writing it as VC. So look at the voltage across the 4 ohm resistor. Well, it has to be, so here I go. I'm going to focus on this term. This guy has to be, it's voltage divided by resistance, so it's going to be VC divided by 4. Then my inductor current is good. I got to worry about my cap of the C here. So you could see here is that this guy is 1/4. And since I've learned my lessons from the last one, I'm going to write this as 1/4. And now what I'm going to do here is that I'm going to collect the VC terms. And you could see that this should read 1/4, 1 plus S hat, VC plus IL. Now I'm finally going to put my current there. So here I go. This is what KCl tells me. Let's go do KVL. So if I look at KVL, we're looking to connect these guys right here. And we already said that we're going to do the right loop to get the KVL to connect VL and IC. So here we go. So look at that. VC has to equal the voltage across the 6 ohm plus the voltage across the inductor. So look what I got to do. I got to convert V6 and I got to convert VL. But what I'm going to do here is that I'm going to bring them to the other side here. So look what I get. I get VC. Now let's focus on this guy. Look at the 6 is in series with the inductor, so they must have the same current. So I'm going to write this as minus 6IL, right? That's where I got this guy from. Now look at the inductor. The inductor here is a 1 Henry, so this should be minus 1 times SIL. And note that all of this is equal to 0. So then I'm going to clean this up and I'm going to combine the IL terms. So this should then equal VC minus 6 plus S hat IL equals to 0. Okay, so here I go. Now I got 2 equations, 2 unknowns. Let's now write the operator equation. So what are we solving for? I don't even know. Again, we're looking at the inductor current. So I got to solve for IL. So let me set this up. So then this tells me here, I got to collect VC terms. So from the first one, you could see that I'm going to write 1/4, 1 plus S hat. Then I get 1. Then the I term, I'm going to get minus 6 plus S hat. And then I'm going to get a 1 here. So this is my what? My operator equation. So you could see that whether I have a cap or an inductor, I'm always going to get the same operator matrix. That's where I get my natural response. Now let's look at the force response. Remember, this is IL, so that means I got to get this guy. So I take my constant terms. What's my constant terms? Ooh, I didn't write that out, did I? Let me move this out here a little bit. So then my constant terms should be what? It should be, since I'm looking at the IL term, it should be 1/4, 1 plus S hat, 1, and then now I replace this guy like that. And again, I was going to multiply that out. So that's how I get my operator equation. This is what it looks like. And then my constant term, when I look at, if I do the cross product, look at that. If I'm looking at the right side of the equation, you could see I get 1/4 times the quantity 1 plus S hat times 0, that's 0. Then I'm going to get minus 5. Okay. So let's go calculate this matrix equation. So if I calculate this matrix equation, I got to do the cross multiplication. So I'm going to go 1/4, 1 plus S hat times 6 plus S hat with the minus sign. And then I got to multiply these by together. So I get minus 1 times 1, which is 1. This is operating on IL, and this is equal to minus 5. Right away, you could see that I get 0 here, 0 here, 0 here. There's no minus signs. So let's go clean this up. So now I want to write this out. So the first thing I'm going to do here is I'm going to go after the square term. So look at the S squared term here, S squared term here. So I'm going to get 1/4 S hat squared. Now I got to get my constant terms now, my S terms. So there should be 2 of them. So look at that. I get S times that, and then I'm going to get S times 1. So if I do that, I'm going to get S times 6. So I'm going to get 6. And then the other way, I'm going to get plus 1 S hat. And then I got to multiply this by 1/4, which I forgot to do. So I got to move this over. And then I have my 1/4 here. And then at last I get plus 1. Okay, so this is IL. Let me clean this up, times 5. So what I'm going to do here is I'm going to multiply everything by 4. Okay, so multiply everything by 4. If I do that, I'm going to get S hat squared, S hat plus 4, and that should be 20. Let's say that this is it. Let's go check it, assuming I didn't do anything silly. Okay, so here's my second order equation. So now let's go do the check. So the check here is that we know that IL at infinity, the force response is going to be a constant, which is B. So the first term is going to give me 0. The second term is going to give me 0 plus 4B equals to 20. That tells me that the final current value should be 20 divided by 4, so it should be 5 amps. Let's go check it with the circuit. So if I go and I check it with the circuit, you know what? I should really just get a copy of this circuit here. Let me go into my notes and see if I can get that. So we don't have to keep dragging up and back and forth. Better for documentation. So what I'm going to do here is that I'm going to put the circuit right there. So look what happens. Oh, let's see. So this guy becomes an open. So if this guy becomes an open, we know that the current in this circuit here, IC, is going to be equal to 0 since this will be an open. So there's no cap, no current there. This guy becomes a short. So we can see here is that the current of this guy is IL right there, but it's a short. So what I'm seeing here is that IL at infinity should be IL6 at infinity. So if I use the current divider rule, it should be 4. So to get the current of the 6, it's got to be the opposite resistance plus 4 plus 6 times 5. So what am I getting here? I'm getting 20 divided by 10. Wow, I am not getting that result. Am I doing something silly? 20 divided by 10 is 2. I'm getting 2 amps. This tells me that I have a problem. Where's my, let's look at my algebra here. So I have a problem in my equation. Let me go and look at this equation right here real quick. Let's go back and look at the KCL.
Hey, Carlos,
Yeah?
I think it's where when you're simplifying the operator equation, I think we forgot to add the constant. So when you have 1 plus s hat times 6 plus s hat, we forgot that 7 term that comes out of that.
So are you talking this 7 term right here?
So well, we'll know when we just have 1 times 6, right? Because we multiply that.
Oh, shoot. You're absolutely right. I forgot to do the constant term. Yeah. Right? This is Josh's correction. And it's really right in here. So when you look at this thing, I have 1/4 of 1 plus s hat, 6 plus s hat, plus 1. So when I go and I do that, I do get a 4th s hat squared plus a 4th times 7 s hat. But then I forgot to do 1 times 6 plus 1. And when you do that, so then if you then multiply by 4, throughout, you could see here that then I'm going to get s hat squared plus 7s hat, and then I'm going to get 6 plus 4, which is then, of course, s hat squared plus 7 plus 10. Oops, I forgot to put the s. And then I get IL, which will then be equal to 20. So there's an algebra mistake that Josh picked up on. So then if I now go look at the, so now if I do my check, you could see here is that IL of infinity, which is B, then tells us that I get 0 plus 0 plus 10B equal to 20, which then gives us that B is equal to 2 amps. And you could see here that these two then match. And because they match, then that means that that equation is correct. And so that means that this guy is not correct. So let's go calculate the characteristic roots of this guy now. So if I go calculate the characteristic roots of these guys, what we're going to see here is that now I start step 2.1. And 2.1 says I need to determine characteristic roots. So if I do that, all I do is I go right from our matrix operator, right? So I take my operator matrix, and get characteristic equation. So then I get s squared plus 7s plus 10 has to equal to 0. Again, can I pick this thing off? I can't pick it off. So I typically do this guy right here. Unless it's real obvious. So then this tells me here, then I could see here is that 2 alpha must be 7 and omega naught must be 10. So I got to get so when I look at this thing, this tells me here is that alpha is 3.5. What's omega naught has to be less than that, right? What's the square root of 10? I don't know what that is.
3.16.
What is it?
3.16.
Okay, 3.16. So then that means here, immediately we can see here is that alpha is greater than omega naught. So therefore it's overdamped. The problem is that now you got to go calculate the damn S1 and S2. Okay, so now we know what that is. So that means here, I got to go calculate those roots. Shoot.
2 and 5.
You know what? Can't you can break this up. Oh, why didn't I see that? Right? We can get the root by inspection. Right? Because I can write S, right? That's got to be 2 and 5. Shoot, I wouldn't have done that, but now that I did it, right? So this tells us that S1 and S2 must be -2 and -5, right? We know what those roots are. So then that means here is that now we have the, if I go to step 2, so typically I just write step 2 and step 3, but in the beginning I just wanted to do this. That means write out natural and general response. So in this case, I would come in here and I would go, okay, for the inductor, I need the natural response, and I also need the force response from step 1. So the natural response has to be, it's got to be A1 e to the minus 2t plus A2 e to the minus 5t. That's my natural response right here. And then my force response, we already saw, was what? B right here, which is 2. So then I write 2 here. So now I have my general response. And you could see that we're setting it up to solve for A1 and A2 here. Okay, let's go to the next one.
Oh, wait, Carlos, is B 2 or 20?
Is it 20? I think it was 2.
Wait, do we plug in at infinity then?
Yeah, it has to be at infinity
Oh, okay.
because that's the force response. You're forcing the components to go there.
Right. Oh, okay. Got it. Thank you.
Now note, I am making mistakes. And that's because I think in my case here, I'm just trying to do too much too fast.
Yeah, no, I was just confused on that. Thanks for clearing that up.
No, I'm not talking about you. I'm just talking about in general deriving these things. And I'm trying to really work on you with this here. So let's go look at this thing. We always write the circuit for t equal to 0 plus. So you could see that all the stuff from left of the switch doesn't count. So what I'm seeing here is that I have my inductor current, my 1 ohm resistor, my VC, oh, my IC, excuse me. So you could see that I only have one node here, right? And then of course my other node is going to be my ground. So here we go. Let's apply KCL. And then I apply KVL. And let's do that. So there's only one node, so they're all parallel. So that means all of those currents, which is the direction of current? Well, I'm going to call this my VC node right here. You could see that they all have polarity. Check out the currents. This should be IL. All of the currents are going to the ground. I1 ohm plus IC have to equal to 0. Now I'm going to convert these guys. So look at the VC. So, excuse me, the IC. I get a quarter, so I should have a quarter S hat VC. And then look at my 1 ohm resistor. There's only one resistor, so I'm going to convert that. So then this should be just VC. And then I look at my inductor current, and I get IL. So if I then clean this up, I'm going to go 1 plus 1/4 S hat VC plus IL equals to 0. Okay, let's keep going. So for KVL, we could see here's that the voltage of the cap must be the voltage of the inductor. So VC must equal VL. In other words, I can write this. Now I'm going to convert the inductor voltage, which is a 2. So this should be 2 S hat IL equals to 0. Here's my second equation right here. So now I'm going to go in and I'm going to do up the matrix here. So if I do up the matrix, I'm going to combine my VC terms. Right, there's my VC terms, and then this guy's going to give me 1. This guy's going to give me 1, and this guy's going to give me minus 2 S hat. And then I'm going to get VC, IL, and then I'm going to get my constants, which is 0, 0. So here we go. So we now know that this is my operator matrix that gives me my natural response. So this tells me here, let's do the cross here. So if I do that, this is going to give me minus 2 S hat operating on 1 plus 1/4. Oops. Right, and then my cross term, which will give me minus 1, that's going to be VC. Now look at my zeros. So then I'm going to get 1 plus 1/4 S, 1, and then I got 0, 0, which is of course 0. Let's clean this up. So see the minus signs? I'm going to get rid of all the minus signs. So here's my term. So my first term, I'm going to multiply this guy times that guy. So then I'm going to get 2 times a quarter. So I'm going to get 1/2 s hat squared. Then I'm going to multiply by the second, which will give me 2 s hat plus 1 VC equal to 0. I'm going to multiply the 2 out. So I'm going to get s hat squared plus 4 s hat plus 2 VC equals to 0. So now I have my second order differential equation. So now what I got to do is I got to go get the roots. No, we should check this thing. Well, if I check this thing, look at this thing. There's no source in the circuit, right? So there's no source. That implies that VC at infinity must equal to 0. And you could see if I punch this into the equation, that tells me here is that VC at infinity should be 0. So for right now, this equation checks out. You know what? I'm over my time. I'm over my time. So, damn, I made a couple of mistakes there. I'm not happy about that because that cost me in not finishing this example. I'll pick this up on Wednesday. You could see that it's getting intense here. And by the way, we still have 3 more steps on the problem solving. We're not even halfway through the problems. So, okay, I'll talk to you guys on Tuesday or Wednesday. Okay, later on.
Thanks, Carlos. See ya.
Thank you.